This presentation is about tolerance stacks, and particularly statistical tolerancing. An earlier presentation explained why you need Tolcap for checking and setting the tolerances you put on drawings. If Tolcap is good for individual tolerances, then hopefully you'll see that Tolcap is, well, essential for tolerances in combination, in tolerance stacks. Statistical tolerancing is almost always misapplied. We'll have a look shortly at why statistical tolerancing is invoked and how it is usually applied with no consideration of any underlying assumptions. In fact, there's a general lack of awareness that there are any underlying assumptions. Tolerance stacks are not easy. The theory is essentially maths, and I apologise in advance, but the explanation will involve some maths, but it really isn't very advanced, and I will take it slowly. It is necessary to be able to explain the assumptions of statistical tolerancing, why Tolcap is vital for valid statistical tolerancing, and to show a straightforward method of calculating a sound statistical stack tolerance using Tolcap. First, let's look at what we mean by a tolerance stack. We set tolerances for components, but it is often necessary to ensure the parts fit properly when they're assembled together. The diagram represents an assembly. 3 blocks, dimensioned D1 plus or minus T1, D2 plus or minus T2, and D3 plus or minus T3, are fitted side by side into a cradle dimensioned D4 plus or minus T4. Will they fit? Okay, this example looks unrealistically simple, and your real designs will be more complex, but often they do essentially reduce to this problem statement. Clearly, we need D4 to be greater than D1 plus D2 plus D3 to allow for the blocks being larger than nominal size. But if the difference is too large, the assembly may be too slack when the blocks are smaller than nominal. So what should we specify for D4? Always start with a worst case analysis. The assembly will always fit if the parts are in tolerance and if D4 minus T4 is greater than D1 plus T1 plus D2 plus T2 plus D3 plus T3. Or rearranging that, D4 is D1 plus D2 plus D3 plus T1 plus T2 plus T3 plus T4. Note we add T4. More often than not, when the dimensions are at the opposite end of the tolerance band, the assembly would be unacceptably slack. When all the dimensions come out on nominal, the gap is the sum of the tolerances, and when D4 is at maximum tolerance and the block's on minimum, the gap is twice the sum of the tolerances. At this point, someone will usually say, let's use statistical tolerancing. We don't have to add up the individual tolerances. Statistical tolerancing lets you root sum square them. That is, square them all, add up the squares up and take the square root. So now D4 equals D1 plus D2 plus D3 plus the square root of T1 squared plus T2 squared plus T3 squared plus T4 squared. This gives a smaller answer for D4, so less slack. But is it justified? We know that root sum squaring numbers gives a smaller answer than just adding them up. Pythagoras knew that. We can see it's a shorter distance along the hypotenuse of a right-angled triangle than going round the other two sides. But does it mean anything in this situation? The basis of statistical tolerancing is, as I said, a mathematical theorem. Suppose we want to make up a variable, let's call it a stack, is constructed by adding or subtracting a number of component variables that are all independent. That means the value of one variable is not in any way related to any of the others. And further, suppose the probability of finding a particular value of the variable obeys a normal or Gaussian distribution with mean x bar and standard deviation sigma I. Now, it's a property of a normal distribution that if you do add or subtract variables that are independent and normally distributed, as we want to do to make up this variable stack, then the result follows a normal distribution. Further, this variable would have a mean, which is the sum of the component means, and a standard deviation, which is the root sum square of the component standard deviations. The means have to be added algebraically, that is, added or subtracted as appropriate, but the sigma squareds, of course, all add. So that's the theory. If we could travel forward in time, we could measure the dimensions of the components in the stack, assure ourselves they are indeed independent, check that they're normally distributed, and measure x bar and sigma for each one. Then we could properly calculate the stack tolerance. And if our tolerances happen to be the same multiple of the sigmas, and if all the means come out at the nominal dimension, then root sum squaring the tolerances will work. But how do we know that? And if we don't know that, and ask again how could we know, there's no justification for root sum squaring. But we have Tolcap. If your head hurts, this might be a good point to pause this presentation and walk around the office. Okay, if you're back now, let's continue to use the same example to explore and try and understand the traditional approach to statistical tolerancing, and then we'll take a look at a method for calculating stack tolerances using Tolcap. We'll compare and explore how stack tolerances are calculated as a function of the component tolerances. T-stack is a function of the individual tolerances. That just means that there's some equation, such as T-stack is the root of the sum of the tolerances squared, which just means square each of the tolerances, add them all together, and then take the square root. The algorithms or equations will be given and explained in the general case, but it's helpful to compare approaches. Purely to do that, we will take the specific if implausible case where all the component tolerances happen to come out equal. So T1 equals T2 equals T3 equals T4, and it equals T. This is done just to make the comparison computations easy, and let's call that stack T star stack. The following slides will use some math, so let's get some of the manipulations clear and out of the way. As explained above, sigma di means add up all the values, and don't forget there may be plus or minus. So in our example, to calculate the normal gap, sigma di equals minus d1 minus d2 minus d3 plus d4. Recall that root big sigma squared means square all the sigmas, add them all up, no minuses unfortunately, and take the square root of the sum. Note that if we have a constant inside the expression, root sum the sigma square, c times the sigma squares, that is equal to, you can put the c squared outside the sigma, or you can bring the c entirely outside of the brackets. That piece of maths enables us to say that if, for example, Ti happens to be 6 sigma I, then the root sum square of the sigmas equals the root sum square of the tolerances divided by 6. Or even the root sum square of 4.5 times the sigmas squared equals the root sum square of the tolerances times the 4.5 over the 6. Finally, for the purpose of comparative example, note that for 4 equal tolerances, T1 equals T2 is T3 is T4, then sigma Ti is 4T, but sigma Ti squared, root sigma Ti squared is 2T. When statistical tolerancing was conceived, a tolerance of just 3 sigma was considered entirely adequate. Assuming component tolerances were set at 3 sigma, a 3 sigma stack tolerance was calculated as square root of the sum of the tolerances squared. This procedure was found to give optimistic results, and in 1962 Arthur Bender Jr. published a paper which proposed adding 50% margin to the stack tolerance. Thus T-stack is 1.5 times the root sum square of the tolerances, and benderizing is still a mainline traditional approach. Tolcap predicts CPK rather than sigma, but we can readily make use of Tolcap to analyse the traditional method and then look at how it can be developed and improved. While traditional statistical tolerancing works with 3 sigma tolerances, let's start from the rather more up-to-date design for 6 sigma. DFSS says to set the tolerance to 6 sigma to allow 1.5 sigma for the process shift, i.e. to allow for the other assumption of the maths of normal distributions that the mean of the parts may not match the nominal dimension. Does this mean that the process shift for every manufacturing process really is 1.5 sigma? No, there's no law of nature that would cause that. It's actually derived from the cunning of the manufacturing people. The shift should be less than 1.5 sigma, but if necessary, a shift any greater than that could be detected in production using a 4-sample X-bar R control chart. A control chart cannot be too commonly required, so this implies that 1.5 sigma is generally sufficient. The empirical data in Tolcap reflects the reality of the various manufacturing processes and confirms that 1.5 sigma is sufficient, but not always necessary. The process shift in Tolcap may be as much as 1.5 sigma, but it will be smaller if appropriate to the process. Extracting the process shift from Tolcap is no simple matter. It varies across the maps, and the effect of the wizards depends on which issues are being compensated. Allowing for a different material will most probably have a very different effect from compensating for difficult geometry. So let's use Tolcap, taking the 6 sigma approach, that is, that 1.5 sigma gives a reasonably conservatively large process shift. And that's for now. Later on we can do a sensitivity analysis to show what happens when the process shift is in fact less than 1.5 sigma. To analyse the tolerancing algorithms, we will get our tolerances from Tolcap. We'll use Tolcap in the mode to find the tolerance we need to achieve a target process capability. We want sigma values for these tolerances. Let's start, as I said, with the 6 sigma approach on tolerances. Open Tolcap, select a map, and select CPK rather than tolerance. Enter the nominal dimension. Set the target CPK to 1.5. Apply the wizards and find what tolerance Tolcap gives. Repeat that for each tolerance stack. Now we can analyse the traditional approach. Assume Tolcap has given us 6 sigma tolerances. Each Ti is 6 sigma I. 4.5 sigma I to give CPK is 1.5 plus 1.5 sigma process shift. So if we did want 3 sigma tolerances for the traditional approach, we could halve the 6 sigma tolerances and get 3 sigma is Ti over 2. Our 3 sigma stack tolerances then, T stack is the root sum square of half the tolerances squared, or 0.5 the root sum square of the tolerances. The benderized tolerance would be 50% larger, i.e. 0.75 the root sum square of the tolerances. And in the specific comparison case where all the tolerances are equal, remembering that sigma Ti squared, root sigma Ti squared, is 2t, T star stack is that square root sum square of half the tolerances equals 2t over 2, which comes to t, and the benderized tolerance will be 1.5t. But do remember that t is a 6 sigma component tolerance, And don't we want a 6 sigma stack tolerance to go with that? So how could we work out a 6 sigma stack tolerance? Maybe we just root sum square the component tolerances. That works for components. And then T stack would be the root sum square of the tolerances. And for equal tolerances, that T star stack would come out to 2T. Or maybe we still need to benderize the tolerance. Do we need the full 50% extra? T star stack would then come out at 3T. Or is the traditional absolute correction for 3 sigma tolerances enough? That would be an extra 25%. So T star stack would be 2.5T. To find out which, we're going to need to look at the process shift allowance more closely. And this may be again another good time to take a pause and clear your head, and then I'll tell you how we do that. Okay, let's look at the process shift allowance more closely. The process shift recognises that the mean dimension of the part is not necessarily equal to the nominal dimension on the drawing. Thinking real process shifts, for some processes such as turning, the shift will depend on how well the setter has set up the batch. For processes such as moulding, the process shift will to a large extent drift over time as the tool wears. So the process shift includes at least an element which is not variable from part to part, but fixed from batch to batch or drifts very slowly over time. So, while it makes sense to root sum square the random part element of the tolerances, providing they are independent and normal, it may be prudent to combine the process shifts worst case and simply add them up, rather than root sum square them. On this basis, if our 6 sigma tolerance Ti is 6 sigma i, the process shift is 1.5 sigma i, which is a quarter of the tolerance. Part-to-part variation is 4.5 sigma i, which is 3/4 of the tolerance. Then the T stack would be the sum of the quarters of the tolerances plus the root sum square of 3/4 of the tolerances. Simplifying the equation to make the computation easier using the bit of maths we did before, T stack is sum of the tolerances times a quarter plus the root sum square of the tolerances times 3/4. And in the specific comparison case where all the tolerances are equal, T star stack comes out to be 2.5T. And it's tempting to say that this lines up with one of our benderized projections, but remember that this is a special artificial example that happens to use 4 components. But here at last is a method. Find 6 sigma tolerances from Tolcap, add 1/4 the sum of the tolerances to 3/4 the root sum square of the tolerances. Now for a sensitivity in the analysis. The analysis above assumed a design for 6 sigma 1.5 sigma process shift in the tolerances obtained from Tolcap. If we knew the process shifts were smaller, we would modify our calculation. For example, suppose the data in Tolcap reflected only 0.5 sigma process shifts for all the components of the stack. Then a CPK equals 1.5 tolerance will comprise 4.5 sigma for the short-term variation plus only 0.5 sigma for the process shift. A 5 sigma tolerance where we expected a 6 sigma tolerance. What's the effect of this? Well, the process shift at 0.5 sigma is now the tolerance divided by 10, and the part-to-part 4.5 sigma is 9/10 of the tolerance. And now the T stack is the sum of the 10th of the tolerance and the root sum square of 9/10 of the tolerance, which comes out to 0.1 of the sum of the tolerances and 0.9 of the root sum square of the tolerances. And then if we go to the specific comparison case where all the tolerances are equal, that comes out to T star stack at 2.2 times the tolerance. Of course, we didn't know we had a 5 sigma tolerance, but we can have some confidence that our computation assuming Ti is 6 sigma i is conservative, and the margin in T star stack would be 12%. If there were processes such that all the component process shifts were 0, then each Ti would be 4.5 sigma, and we would want to simply root sum square the tolerances. In this case, we would find T star stack is 2T, and the margin in T star stack would be 20%. The analysis used can readily be applied to Tolcap's default CPK is 1.33 tolerances. For the same process and dimension as in the 6 sigma case, we still assume the process shifts are 1.5 sigma. And for CPK is 1.33, our tolerance needs another 4 sigma for part-to-part variation. So now this is designed for 5.5 sigma. So Ti is 5.5 sigma, 1.5 sigma I is 3/11ths of Ti, and 4 sigma is 8/11ths of Ti. So the T stack comes to be 3/11ths of the sum of the tolerances and 8/11ths of the root sum square of the tolerances. So we have a simple algorithm for tolerance stacks with a minimum CPK is 1.5 or CPK is 1.33 to match our component CPK. We hope this presentation has explained the assumptions of statistical tolerancing, why Tolcap is vital for valid statistical tolerancing, and a straightforward method of calculating a sound statistical stack tolerance using Tolcap. For 6 sigma tolerances, use Tolcap to set component tolerances at CPK is 1.5, and then T stack is 1/4 of the sum of the tolerances plus 3/4 of the root sum square of the tolerances. For Tolcap default CPK is 1.33 tolerances, use Tolcap to set component tolerances at CPK at 1.33, and then T stack is 3/11ths of the sum of the tolerances plus 8/11ths of the root sum square of the tolerances. Thank you for listening, and for more information visit www.tolcap.com.